Okay. Howdy, everyone. How are y'all this fine morning? Doing good, doing good. It's a little chilly today, but this weather's been weird. I cannot make up its mind. So I just sent out an email if you haven't seen it. So homework number 2's been posted. Sorry for the delay on that. It took a bit of time to get it in. So it's going to be due on Sunday now because of the delay. Yes. Oh my God. Minor detail. Yes. Thank you. I am fixing that right this second. You're absolutely right. I just realized. Yep. As soon as you said that, I was like, yep, that's exactly what happened. Now it should be. Now it should be. Okay, there we go. Should be viewable now. So that'll be due on Sunday. The PDF says Friday. Ignore. It's due on Sunday. So that's going to cover up to Green's theorem. So there's a quiz which I will have available tomorrow. You know what? No. I'm going to make the quiz. I'm going to make the quiz available Saturday. I think that's only fair. That was, yeah. So the quiz will be on Saturday. And that will cover the conservative vector fields and then surface integrals of scalar functions and also vector fields. It will not cover Green's theorem, which is on the homework. But it'll cover everything up until then. Can I make the quiz both Friday and Saturday? Yeah. I could do that too. Yeah, sure. Let me write that down. Yeah, I will do that then. Cool. Yep. And also I finally got in, well, not everything, but I've released the notes, the actual grading bit of the previous quiz. So you should be able to see that. And I will upload a key in a bit. I'm making sure. There's someone I haven't heard from yet, so I don't want to upload a key yet, but I will do that for the quiz. 16.3 to 16.5. Yes, it does. Correct, Elizabeth. The quiz does. The homework covers 17.1 also, which we're finishing up today. But yes. Okay. All right. So let's continue talking about Green's theorem. The first of our big integral theorems that we close the course out with. All right. So just a reminder. So suppose C is a simple, and by simple closed, so C is going to be a closed curve. When we say it's a simple closed curve, that just means it doesn't intersect itself. So let me say also it is counterclockwise. So it's a simple counterclockwise oriented closed curve. And D is going to be the region enclosed by C. So there's our curve C. It is counterclockwise oriented. And D is going to be the region enclosed. So simple just means it's not self-intersecting like this. Right, so this would not be simple. This is simple, doesn't intersect itself. Okay, so if that is the case, then Green's theorem says, this is worse than usual. Let me turn tablet mode on. That is awful. Okay. So Green's theorem says the integral around, let me suppose our vector field F is F1, F2. And of course, this all needs to be in R2. Need to emphasize that. Green's theorem is valid only in R2. Wow, the region enclosed by C. That is a lot of arrows in there. Okay. So the integral over C of the vector field F, and often we see it written as, these mean the same thing. They're just different ways of writing them. The integral of F1 dx plus F2 dy. Remember, if you see a line integral written like that, you want to think the integral of a vector field, F1, F2. By Green's theorem, that is equal to the double integral over the region D of the partial of F2 with respect to x minus the partial of F1 with respect to y. So the first two guys are just different ways to write the same thing. But Green's theorem says the line integral of a vector field f1, f2 around a counterclockwise simple closed curve is equal to the double integral over the enclosed region of the partial of f2 with respect to x minus the partial of f1 with respect to y. And the way we remember this is if f is conservative, we know the integral around a closed curve is 0. And the way we check that it's conservative, I'll draw an arrow in a second, is we check the cross partials condition, and these are exactly the two partials there. So just bring the df1 dy over, subtract from both sides, and we get that that's equal to 0. And so we're integrating 0 over d, and so the integral is 0. And that's the way we can remember that df2 dx minus df1 dy bit. Just remember the x guy comes first. Okay, so that is Green's theorem. One thing I want to mention, the orientation of the boundary curve C is important. It has to be clockwise or counterclockwise oriented. If it's not counterclockwise oriented, we need to change the sign of our integral on both sides of the equation. We'll see an example of that. But yes. Okay, so that's Green's theorem. Let's do some examples. Okay. So let's evaluate the integral around the closed curve C of the vector field F, where here F is going to be sine x, x squared y cubed, and then I will draw a picture of C. C is the following triangular curve. So with vertices at 0, 0, 2, 0, 2, 2, and we're going around it this way. Okay. All right. So Green's theorem, pretty much every time on an exam where you see an integral around a closed curve in R2, you're going to want to use Green's theorem. And that is basically 100% of the time. That's what we want to happen. Okay. So really, there are a couple reasons for this. So either the curve in question is going to lead to a lot of integrals or a nasty integral. So the curve here is, it's a triangular curve, right? And so if we did the line integral here, we would have to parameterize each side of the triangle, and we'd be performing 3 line integrals, and nobody's got time for that, honestly. But if we use Green's theorem, we can turn it into a single one double integral, which is much more convenient. Secondly, another thing that can happen, and this can happen in conjunction with the first, is that the vector field can be completely disgusting, and evaluating the line integral directly could be awful or impossible. But using Green's theorem, we're taking derivatives of stuff, and often the disgusting terms get killed off, and we're left with a much simpler double integral. But Green's theorem basically always, in R2, you see a line integral over a closed curve. Think Green's theorem every time. And that's basically how Green's theorem always works. Start with the line integral, turn it into a double integral. Okay. We'll do an example in just a sec that goes the opposite, but that's the exception rather than the rule. Okay. Okay, so first order of business for Green's theorem, we need our boundary curve to have the correct orientation. So we need the boundary, we're going to let D be the enclosed region here, the enclosed triangular region. For Green's theorem to work, what do we need to be true of the boundary curve? What does the orientation need to be? So it needs to be counterclockwise. Is our curve counterclockwise? Well, yes, it does need to be closed, correct. But it needs to be counterclockwise oriented. This is actually clockwise oriented. So this should be the first thing you check always. Okay, so the boundary curve's not counterclockwise. So what we're going to do is we're going to turn it into a counterclockwise oriented thing. But in doing so, we're going to flip the sign of the integral. So here's what we're going to do. The integral over C, we can't use that directly to do Green's theorem, but what we can do is we can switch the orientation of C. We can take negative C, right? Remember, when we say negative C, that just means the same curve, but we're orienting the opposite way. So that's fine, but when we switch the sign of the orientation, when we switch the orientation, we switch the sign of the integral. So we need to multiply it by -1 to make it work, to get the same thing. So we want the integral over the curve C. To use Green's theorem, we need to flip the orientation of C so it's going counterclockwise, but then we also need to multiply it by -1 to get the correct sign. Does that make sense, right? If we flip the orientation, we change the sign. So to change it back, we need to multiply it by negative again. That's fine. Okay, so now we have our boundary curve is counterclockwise oriented, and we can use Green's theorem. So by Green's theorem, that's the integral over the enclosed region of the partial of f2 with respect to x minus the partial of f1 with respect to y. But we have this negative in front because we multiplied the other guy by a negative. Right, so if you get rid of the negative signs, that's just Green's theorem. And you can multiply both sides of an equation by -1. That's fine. So does everyone follow so far?
And I have a quick question.
Yes.
So how does the negative c affect that last equation we just wrote there?
So the negative c doesn't affect it. It's just in order to, because this is what we actually want to calculate. And in order to get this, we need to multiply that line integral by a negative to get the right sign. But if we ignore that, if we ignore the negatives, we have Green's theorem, and then we just multiply both guys by the negative. So what we're actually going to calculate is this guy here, and then we're just going to multiply it by a negative. If you like, you can bring that negative inside, and you get df1 dy minus df2 dx. But it doesn't matter. But does that make sense?
Yeah, thank you.
Okay, so let's actually calculate that. Okay, so let's find our bounds for D. Oops. Let's do it this way. Let's find our bounds for D, because we're calculating a double integral. And then we will write down the df2 dx minus df1 dy. Okay, so D's, we're just doing a double integral. Is D a, how do we want to treat this? Do we want to do top curve, bottom curve, left curve, right curve, polar? How shall we integrate this? We could do left, right. That's fine. This is horizontally simple. It's also vertically simple. And if I can do top and bottom curve, I prefer doing, but that's just personal preference. But I'm going to say we have a top curve and a bottom curve. So the bottom curve is y equals 0. Why is it doing that? The top curve is y equals x. So x goes from, or y goes from 0 to x. And the bounds for x goes from 0 to 2. If you like, you could say x, there's a left and a right curve. So the left curve would be x equals y. Right curve would be x equals 2. And then y would go from 0 to 2. That works just as well. So remember, our f was sine x, x squared y cubed. So let's put in the bounds. And let's remember this minus sign. Oh my God, why does it do that? Let's remember this minus sign out in front. So y goes from 0 to x goes from 0 to 2. Okay. So what is the partial of f2 with respect to x? So that's our f1. This is our f2. So we get 2xy cubed. And the partial of f1 with respect to y is 0. Oops, that's okay. So
So
now
how
we
do
have double integral. This is a very simple
F1?
double integral. I'm sorry.
So how do we know which one's like F1 and F2?
So f1 is just the first component. F2 is the second component of the vector field.
Okay, sorry about that. I thought x squared and y cubed was separate.
No. Yeah, so that's one term.
Okay,
Yeah.
cool.
Yeah. Okay, and that's a very simple integral. So remember that negative sign. If you don't want to forget the negative sign, you could also bring it inside and flip the thing inside, just to remind yourself. But what we end up getting is 16/3 for the integral, and then we multiply it by -1. So we get -16/3. Yeah. So I gave the curve at the beginning, Quan. Yeah. Yeah. Okay. So I want to make sure no one's confused about the negative sign. Does everyone see why I had to multiply by a negative? So for Green's theorem to work, the boundary curve, the closed curve you're integrating over, it needs to be counterclockwise oriented. We were clockwise oriented, so we needed to flip the curve and then multiply by a negative to do Green's theorem. Really, if your orientation's wrong, you just need to multiply everything by a negative, and that'll fix it. Okay. So let's do an example of, so that's almost always how Green's theorem works. Start with the line integral over a closed curve in R2, turn it into a double integral. The double integral is going to be easier to deal with, almost always. And that's almost how Green's theorem works. But we can go the other direction. We can start with a double integral. In this case, often it's area. So remember, the area of a region D is just equal to the double integral, the integral of 1 over the region D with respect to area. Oh, that's a bad picture. So suppose this is our region D, and we wanted to calculate the area. What we could do is we could use Green's theorem backwards. If we say, okay, C is the counterclockwise oriented boundary curve, if we can find a vector field F, So if we can find a vector field F1, F2, such that the partial of F2 with respect to X minus the partial of F1 with respect to Y is equal to 1, right? Our integrand here. Then we can use Green's theorem to calculate the area by integrating that vector field F over the boundary curve. So then by Green's, the area, which is the integral of over the region D of 1, is equal to the integral over C of the vector field. And so we can calculate that line integral to get the area. Okay, but the thing is, there are infinitely many different vector fields, F1, F2, where when we take the partial of F2 with respect to X minus the partial of F1 with respect to Y, we get 1. There are lots of different ones. For instance, if we consider the vector field 0x, that works, right? The partial of F2 with respect to X is equal to 1. The partial of F1 with respect to Y is equal to 0. Partial of F2 with respect to X minus partial of F1 with respect to Y is 1. Similarly, negative Y, 0 also works. You take those partials, you do the thing, you get 1. Similarly, we could do negative Y over 2, X over 2. Those all work, right? There are infinitely many ones we could use. Some of them will work better than others, but yeah. So typically we don't go this direction because there are infinitely many vector fields you could choose, and you have to come up with a vector field. And sometimes coming up with one that is easy to calculate is difficult. Okay, so let's look at an example of this. So let's use Green's theorem to calculate the area of the ellipse x over a squared plus y over b squared equals 1. Okay, so remember A is going to be the x radius and B is going to be the y radius. We'll call that region D. We want to calculate the area of this ellipse. So what we're going to do is we're going to parameterize the boundary curve counterclockwise oriented boundary curve C. And we're going to use the vector field zero x. In fact, any of these vector fields we wrote here would work equally fine, but we'll use 0x. So by Green's theorem, the area of this ellipse is the integral over the region D of 1 with respect to area. And so by Green's, that's equal to the area over the boundary curve of the vector field F, because the partial of F2 with respect to X minus the partial of F1 with respect to Y is equal to 1, which is the thing we wanted to integrate. That's why we chose this vector field F. Oh. Okay. So let's integrate this vector field over the curve. So first thing we need to do is we need to parameterize our curve C. Okay, so maybe not immediately obvious how we do this, but notice, so the ellipse, the boundary curve is given by x over a squared plus y over b squared equals 1. That's almost a sine-cos relationship directly, right? If we let x be something times cos and y be something times sine, so that when we square the first and the second, we get sine squared plus cos squared, then we would get 1. So we need to figure out what do we need to multiply x by, and what do we need to multiply y by, so that we get sine and cos. So the easy choice here is we're going to let x be a times cos t, and y be b times sine t. And we're going to let t go from 0 to 2 pi. And the reason we do that is because when you divide x by a, you get cos. When you square it, you get cos squared. When you divide y by b, you get sine. And when you square it, you get sine squared. Cos squared plus sine squared always equal to 1. So that's a parameterization for C. And because x is cos and y is sine, we're going around counterclockwise. Okay, so that's our parameterization. Our prime of t is going to be, since we're going to use this for dr, negative a sine t and b cos t. And so let's do our integral. So we get the integral from 0 to 2 pi. So in our vector field F, plugging in the parameterizations for x and y, 0 stays 0. X, we said, is a cos t. So that's our vector field F now. And we dot that with r prime t dt. So r prime t we said is negative a sine t and b cos t. And taking the dot product, we get 0 plus ab cos squared t and so we're integrating cos squared. Remember, cos squared is 1/2 1 plus cos 2t. Let me do this down here. When we integrate that, we get, so ab times 1/2 That's fine. So 1/2 times 1 plus cos 2t integrates to 1/2 t plus 1/4 sine 2t. We go from t equals 0 to 2 pi. And we get ab times 2 pi times 1/2, which is just ab pi. Okay. So not typically how we do Green's theorem, but it is possible to go from a double integral. Specifically, usually it's in the context of area, to turn it into a line integral, which we then calculate. But then you have to come up with a vector field for which the partial of f2 with respect to x minus the partial of f1 with respect to y is equal to the integrand, in this case 1. But this is not typically how we do Green's theorem. This is sort of backwards, but it is possible to do it like this. Any questions about this? Okay, so there is a more general form of Green's theorem. And I don't really have time to do an example here, but that's okay. That's okay. Let me give you the more general form of Green's theorem. Okay, so far we've been looking at regions D enclosed by a single simple closed curve. But suppose we had a region D like this, which has holes inside. So suppose this is our region D. That's terrible. I should do a different color for that. Suppose this is our region D. It consists of a solid region like that, but we've got little holes inside. So now the boundary is more complicated, right? We have an outer boundary curve. Let's say that's C1. But then we have 3 inner boundary curves. In this case, C2, C3, C4. We would like to do a Green's theorem over regions like this, but how do we orient our boundary curves, and then what do we do with the line integral? So here's what we're going to do. So for regions D, with boundary consisting of multiple closed curves. No, let me say it this way. So we're going to orient each as follows. So basically, walk along. So pretend you're an ant walking along your each of these boundary curves. And we're going to orient them so that we're walking in the direction so that you're walking along your boundary curve and D is always on your left. Right, so pretend we're an ant walking along a boundary curve. So in this case, in this example here, if we're walking along, let's orient these guys. So if we're walking along C1, the outer one, and we always want D, the enclosed region, on our left, do we need to be going around clockwise or counterclockwise for the outer guy, C1? We want to go counterclockwise. So the outer boundary curve is always going to be counterclockwise, just like it was before. We're walking around so that it's always on our left. How about the inner guys? So all of those are going to have the same orientation. Do we want to go around counterclockwise or clockwise on the inner guys so that it's always on our left? We want to go around the inner guys clockwise. Sorry, that's really kind of a terrible drawing, but you can also remember that if you like. But I like the walk along so that it's always on your left thing, because when we get to Stokes' theorem, clockwise and counterclockwise will no longer make any sense. So I would use the rule, walk along the outer boundary curve so that D is always on your left. Okay. So we call all the boundary curves with this given orientation the boundary of D. And we write it the fancy D like we do for the partial derivatives. It's the same guy. But we write it as fancy D of big D. And that fancy D means the boundary of. And then that's with that orientation that we gave, where you're always walking along each of those curves. So the boundary consists of multiple curves together, multiple closed curves. So here's the general version of Green's theorem. Whoops. Let me just write this as Green's theorem. This works. This includes the theorem we did before, where there's only a single boundary curve. So if D is some two-dimensional region in R2, with positively oriented, and the positively oriented means you use the rule I just gave. You walk along each of the boundary curves so that D is always on your left. So we have the boundary of D. And suppose it consists of, C1 to Cn, right? The outer boundary curve and then however many inner boundary curves we have. Then Green's theorem says, with some technical stuff that I won't mention, but it says, whoops. Sorry, for the vector field F1, F2. The integral over the boundary of D which we could also see written as F1 dx plus F2 dy is equal to the double integral over the region D of the partial of F2 with respect to x. So this is exactly the same thing as we wrote before, except now the boundary consists of multiple curves. And so really what we're doing is we're integrating over each of those guys and adding them up. So we're integrating over C1, C2, all the way up to Cn. And we're adding all those guys up. Green's theorem says if we integrate the vector field F over all those guys, give them the right orientation, that's equal to the double integral over the enclosed region of the partial of F2 with respect to x minus the partial of F1 with respect to y. And once again, these two guys are just like different ways of writing the same thing. You could see the line integral written either way. Okay. There's an example of this in the book if you want to see this. So it'd be good to look at to understand how we could use this. But this is the more general form. So that would say, for instance, for this guy here, if I wanted to do the line integral over all the boundary curves together with that given orientation, that would, Green's theorem would say, I could just integrate the partial of F2 with respect to x minus the partial of F1 with respect to y over the enclosed region D. Does that, any questions about that? Alrighty, if not, I will move over to the office hours and see you there, or I'll see you tomorrow, and have a good rest of your day. Yes, what is that, Ryan?